Okay, here we go. Section 1, Part B. You can use a calculator this time. Let's do it. All right. Graph of the derivative is here. The function is twice differentiable. F of 1 equals 0. What must be true? So it looks like we're comparing f of 2, f prime of 2, and f double prime of 2. So f prime of 2 is 0. Right? Because this has a point 2 comma 0. F double prime of 2, well, that's going to be the slope here. That's going to be positive. Maybe like positive 1-ish. You just want to find the slope of that. What's f of 2? F of 2 is going to be, let's see here. So we know that f of 1 is equal to 0. So that means if I start here at 1, that's when I have like 0 area under the curve essentially to start. And then if I calculate f of 2, that's going to be the area under the curve here, right? So another way to think of f of 2 is it's the integral from 1 to 2 of f prime of x dx, right? Because this by definition would be f of 2 minus f of 1, but f of 1 is 0. So what is the area under the curve from 1 to 2? Well, it's negative. Area under the curve, it's below the x-axis, so this is going to be negative. So what's the smallest? F of 2. What's in the middle? 0. And so it's looking like the answer is B. Okay, that was kind of a sneaky problem. 32. We got a table of values for f prime. F prime is always increasing. Which of the following statements must be true? So if f prime of x is always increasing, which it looks like it's doing, right? It's going from -2 to -1 to 0 to 1 to 2. But if f prime is increasing, that means that f double prime needs to be positive. We know that for a fact. So does that mean, let's see, what else do we know then? F prime is increasing, so therefore f double prime is positive, which means that f is concave up. Oh, so B is out. It can't be B. Let's see, what else could be true here? Do we have to have an odd function? Well, I don't think we can, right? Because an odd function, it's usually changing concavity at 0. Let's see, f prime is always increasing, so f double, so it's always concave up. So I mean, it could look something like this. That's usually the sign of an even function, right? As soon as we curl back down, so I don't think it can be an odd function. Do we have a relative minimum at 0? I think we do, because the derivative at 0 is 0. So this seems reasonable. This could be a relative minimum. We don't have any inflection points, so it can't be an inflection point. I'm thinking D is probably right. We can't have an inflection point there, right? Because it's concave up always. So I think D is the right answer here. Why are they letting me use a calculator in this section if I don't need a calculator yet? Well, this next one, we've got some decimals. This is looking like we're probably going to need it here. All right, so we've got an ice field that's melting at this rate. T is measured in days. How many acre-feet of this ice field will melt from the beginning of day 1, which is time 0, to the beginning of day 4? Okay, so this is the rate at which it's melting. So to find the total amount that has melted, we simply integrate. We're going to integrate from 0 to 3. This function, 4 minus sine of t cubed dt. Now, we have not talked about how to integrate a function like sine cubed unless you can use u substitution or something, which we can't here. So we got to go to the calculator for this one. Got to go to the calculator. I'm going to go to F3, go down to integrate, type in my function, 4 minus, parenthesis, sine of x. I'm going to do x instead of t. I hope that's fine for people. Sine of x cubed. And then I need to tell which variable, so comma x, comma 0, comma 3. Close off the parenthesis, hit enter. And the answer is, diamond enter. It's thinking. 10.667A. Cool. Let's move on. The figure above shows a graph of a function which has horizontal asymptotes. Which of the following statements are true? Is the derivative negative for x that is positive? So when x is greater than or equal to 0, that means we're looking at the right-hand side of the graph here. Is the derivative negative? Yes, it's decreasing, so that looks good. is the limit as x goes to infinity of f prime of x equal to 0. So this is the graph of f of x. What's happening to the slope as we go off to infinity? The slope is getting closer and closer to 0, it looks like, so that seems true to me. At negative infinity, the slope is also getting closer and closer to 0, not to 3, so that seems false. So I'm thinking it's A, 1 and 2. All right, so here's a function g of x that we're defining. Oh wait, this is the graph of g of x. And we're also defining what g of x is. It's the integral from a to x of f of t dt. Which of the following could be the graph of y equals f prime of x? Okay. What does y equals f prime of x look like? Well, we know that g prime of x, by the second fundamental theorem of calculus, is f of x, right? You just take the x and plug it in for t. That means that g double prime of x is equal to f prime of x. So what does f prime of x look like? It looks like g double prime of x. So this original function here, let's see, it's got 1, 2, 3 turning points. So it's like a 4th degree polynomial that's going downwards. So if I took 2 derivatives of that, I would get a parabola. Right? One derivative would give me a cubic, another one would give me a parabola, and it's got to be opening downwards because of that negative leading coefficient from the get-go. So I'm thinking B is looking good. B's looking pretty good. 36. Okay, we got the x-axis for one side, and the graph of y equals 4 root 16 minus x squared for the outer boundary. X is measured in feet. What is the projected area of the lawn to the nearest square foot? Okay, so we've got the x-axis for one side, and then the graph of this thing for the outer boundary. All right. Hold on. How long has the x-axis for one side? So what does this function look like? Let's see. If I plug in either 8 or negative 8, it's equal to 0. And oh yeah, I guess what I would do is I would like square both sides of this. So y squared equals 16 times 64 minus x squared. That's what happens if you square both sides. And so I think we're going to have an ellipse here. It's looking like an ellipse to me. So y squared equals 16 times 64, whatever that is, minus 16x squared. So therefore 16x squared plus y squared equals whatever 16 times 64 is. This is an ellipse. This is definitely an ellipse. So the graph's going to look something like this, I think. Let's see. So the x-axis is on one side, and the graph is the outer boundary. So it's going to look something like like an ellipse. If you know a thing or two about an ellipse, the area of an ellipse is pi AB, where A and B are your like semi-major and semi-minor axes. If you don't know this, you can just punch it into a calculator. You can calculate this integral. How would I calculate this integral? We would find the integral from negative 8 to 8 of my function, right? 4 root 64 minus x squared. That's probably the better way to do this. So we just punch that into a calculator. Hope we all remember how to do this. Excuse me. F3, integrate. We're going to integrate the function 4 root 64 minus x squared, comma x, comma negative 8, comma 8. Close that parenthesis off, hit enter. And the answer is 128 pi, which is approximately equal to 402.124. Boom. Okay, sweet. Answer C, maybe. All right, next problem. The derivative is given by this. And what value of x is f of x an absolute minimum? Okay, so we already have the derivative here, which is nice. So we could set that equal to 0. E to the x times negative x cubed plus 3x minus 3. I'm going to set this equal to 0 to find my critical points. I'm only looking at numbers between 0 and 5. And since I'm finding an absolute minimum, I need to use the extreme value theorem here, right? So I need to test the endpoints as well as the critical points. So first, let's find these critical points. With my calculator, I'm going to go to F2 solve. And I want to solve the equation e to the x times negative x cubed plus 3x minus 3 equals 0, comma x. busy, it's thinking. Still thinking. Ay, ay, ay. Here we go. So I'm getting an answer of x equals 0.617. Oh, there's just two answers, or 1.623. So I need to test both of those values in the original function and the endpoints as well. However, I don't have the original function. So how can I determine if I have an absolute maximum or not? So I guess you could graph this function, this derivative, to determine where it's, increasing, decreasing, etc. I guess we'll do this. This seems fine, I suppose. So we'll go to y equals, let's type in the function, e to the x times negative x cubed plus 3x minus 3. And let's graph it. Zoom 6. Okay, so here's your derivative. We see our two zeros there at 0.617 and 1.623. So if I'm looking only from 0 to 5, here's 0, here's 5, here's 0.617, here's 1.623, you see that the derivative is negative over here, and then it is positive in the middle, and then it is negative afterwards. And so what this means is that this is a local minimum, and this is a local maximum. How do we know if it's global or not? Or is it one of the endpoints? So my original function is decreasing, and then it's increasing, and then it's decreasing again, right? So the global minimum has to either be this point right here, or it has to be this point over here on the right. So it could look like this, or it could look like this. Right? The global minimum is either at 0.617, which is B, or it's at the endpoint of 5. And how do we determine for sure which one it is? Well, we could integrate, right? We could find the area under the curve and see which one has accumulated the, I guess, most negative area. And if I'm looking at this graph, I see that there's a lot of area between 1.623 and 5. I mean, it's like going off the charts. So it's decreasing a lot. It's going very, very negative, the area under the curve, right? This little, on my graph right here, this little chunk is going to be a little bit of negative area, and then it's going to be mostly canceled out by this positive area, but then I'm getting a ton of negative area down here, which suggests to me that the answer is going to be 5. I'm going to be getting the most negative, in other words, having an absolute minimum at that endpoint of 5. Okay. Another table problem. What's the approximate value of f prime of 4? Well, let's see here. F prime of 4 is the limit as h approaches 0 of f of x plus, f of 4 plus h minus f of 4 all over h, right? And so what does it look like is happening here? So this is going to be the limit as h goes to 0 of what? So as I get really, really close to 4, what is my slope approximately here? So it's like f of 4 plus h. If h is like 0.001, then f of 4 plus h is going to be 1.16016. Then I'm subtracting f of 4, which is 1.15782. And I'm dividing by h, which is 0.001. Okay, so this is approximately equal to this. Just punch this into a calculator. 1.16016 plus 1.15782 divided by 0.001. I'm getting 2.34. Is that an answer? D. Let's go with D. Okay. Next problem. Oh boy, this looks gross. Okay, so n is a positive integer. I want to find this limit. What is this the same thing as? So what are we finding here? It looks to me like we're finding a Riemann sum, kind of, right? It's not obvious, but we're taking the limit as n goes to infinity. So I'm think of n as like the number of rectangles that I'm using to estimate this, and I'm counting more and more of them. And so you see how each term has a 1 over n in it. So that's suggesting to me that delta x is equal to 1 over n. And since I'm using n rectangles, that means that my length is 1. That doesn't really help me because all my integrals, this one goes from 0 to 1, so it's a length of 1. All the other ones go from 1 to 2. So that doesn't really help me too much. What helps me, though, is the function that I'm actually integrating, right? So I'm using the function 1 over 1 plus whatever number I'm plugging in. So like think of it like this. I'm going from like 0 maybe. Actually, no, I'm going from 1 to 2, aren't I? So here's 0, here's 1, here's 2. This would be 1 plus 1 over n. And this would be 1 plus 2 over n, and so on. And so what am I plugging these numbers into? What am I plugging 1 plus 1 over n into? Actually, is that what I'm plugging in? Yeah, correct. So I'm plugging, let's see, oh, is that right? Yeah, so I think I'm just using the function 1 over x. Right, I'm taking, to find my corresponding y values, I'm plugging in 1 plus 1 over n into x, and then I'm plugging 1 plus 2 over n into x, and so on. So I'm using like the right Riemann sum, essentially, as I'm going along here. I don't know what this function looks like, but I'm using the right Riemann sum for the function 1 over x, and I'm going from 1 to 2. So it's looking like b. I think the answer is b. Yeah, let's go with that. We'll come back and discuss if we need to. Okay, so on this interval, we've got two functions that intersect 4 times. Let a, b, c, and d be the x-coordinates of these points so that they're in order. Which of the definite integrals below has the greatest value? Oh, geez, yikes. Okay, so let's do this one graphically. So go to y equals. We're going to do cosine of 2x. And then we're going to do sine of 3x. And then let's graph it. Yeah, seems about right. It's chaos. Okay, let's change the window so we can actually see what's going on here. So x is just going to go from 0 to 5. And y, these are sine and cosine, so just from negative 1 to 1. Which should look nice. So here's cosine of 2x. There's the first intersection, second intersection, third intersection, fourth intersection. Okay. So which of the following definite integrals has the greatest value? So if we integrate from 0 to a, the top function here is the cosine function. The bottom function is the sine function. And so this is going to give us some positive area. We can calculate that area if we need to in just a second, but that looks like a pretty small positive area. It's just the area of this little, not triangle, but triangle-ish looking thing. If we integrate from a to b, now the sine function is on top, minus the cosine function, and that looks like a bigger area to me. So a is out, because this is more positive. It's a bigger area. We could calculate it exactly using the calculator, or some decimal answers to it, to see how approximately big it is. But to me, it looks larger than this first little piece. From b to c, we're doing the sine function, which is now the bottom function. This can be negative, so there's no way that this can be right. And then from c to d, which function is on top? I think we also have the wrong order for that one, right? So this is also going to be pretty negative, if I'm doing that correctly. So let's see here, cosine. Oh wait, no, from c to d. Sorry, no, I think that is the right order now. Did I do this right? I'm losing which one's which. Let's change. How do I change what this looks like? I guess I don't remember how to do that. Okay, so the first piece, we got cosine up top over sine, so it's going to be a little bit positive. Then we got sine over cosine. Oh, but then sine stays on top of cosine. So this is going to be... Oh, wait, sorry, okay. So these two are actually equal. B and C are equal to each other, because the sine function is staying on top of the cosine for both of them, and we got some symmetry going on there. So B and C are the same size. And then for D, the cosine function is back on top again, but this area is huge. This area is very big. And so I think the answer's got to be D. Okay, I think that feels right. All right, we got a disgusting function. It has 1, 0 in the closed interval. The derivative of this point is what? So we got to do two things here. We got to find out where this thing is equal to 0. Tangent of 3 to the x, set it equal to 0. we're going to use the solver to find that point. The derivative at that point is what? Well, we need the derivative, f prime of x. The derivative of tangent is secant squared. So we get secant squared of 3 to the x. And then we have to use the chain rule, multiply by the derivative of 3 to the x, which is 3 to the x times ln of 3. Okay. So we've got many things to do here. First, we need to pull up F2 solve to figure out when the tangent, tangent of 3 to the x is equal to 0. And okay, cool. So x equals 0.91. Oh wait, this times what is happening here? What is this strange notation? Tangent 3 to the x equals 0. Oh geez. Okay. I don't think I'm gonna graph this instead because that was not a pretty looking answer. So we got tangent of 3 to the x. Okay. And we want to find this first 0, so we're going to go to, math, 0. You need to graph the whole thing, apparently. Okay, let's change the window. We only want to go to 1.5, right? 1.4, whatever. We're going to go to 1.5. Graph. Okay, so then we want to find this 0. So we go to math, 0, lower bound, right there looks good, upper bound, right there looks good, 1.04198. Okay, we want to plug that into the derivative. So again, in home, there are probably many ways to do this, but I'm going to do, let's see, so secant squared, so it's 1 divided by the cosine of 3 to the 1.04198 squared times 3 to the 1.04198 times natural log of 3. Okay, what are you not happy with? Oh, what? Oh. Wait, what? What are we not happy with here? Cosine. Oh, I see. Of. You know, in parentheses there. Sorry. Negative. Oh, okay, that's not an answer choice at all. Oh no. Let's see here. Oh, I got that squared in the wrong place, it looks like. .45, 1, cool, C. Oh, man, that was nasty. I missed Desmos. Okay, 42. So here's values in the table again. We're finding the integral from 0 to 6 using the value at the midpoint of each of these subintervals of width 2. Okay. So, so we're doing 3 intervals from 0 to 2, from 2 to 4, from 4 to 6. And so that means that the width, delta x, for each of these is 2, and the heights of each rectangle, we're using midpoints, we're using the y value at 1, 3, and 5. So 0.25, 0.68, and 0.95. And so all we're going to do is add all these numbers together, multiply by 2, and that's going to give us the area of the rectangle. Just punch that into a calculator real quick. 0.25 plus 0.68 plus 0.95, boom, times 2, boom, 3.76. C. Okay, f is continuous, derivative is given to us, which of the following is true about the original function. Okay, f of x always increases or always decreases. Is that true? Well, let's see, we can make a little sign chart, right? what are the critical numbers for this function? In other words, when does cosine of x equal 0, and when does ln of x plus 1 equal 0? Well, ln of x plus 1 equals 0 only when x plus 1 is equal to 1, right? Oops, it is equal 1, because ln of 1 is 0. That means that x has to be 0, but 0 is not in the interval, so that doesn't matter to me. When does cosine equal 0? A lot of times. Let's see. At x equals pi over 2, 3 pi over 2, 5 pi over 2, etc. And we're going to be alternating signs, I think, a lot in there. So I don't think that it always increases or always decreases. I think it's going to be changing its sign quite a bit. Or because the derivative is changing its sign from positive to negative to positive to negative. We could also graph this to verify. Maybe we should do that. So we're going to graph the function cosine of x divided by ln of x plus 1. Let's just zoom 6. Oh no, we only want to go from 2 to 10. Okay, that's fine. Okay, so yeah, you see how the derivative starting at 2 is negative, and then it goes positive a little bit, and then negative again. So since the derivative is changing sign, the function is changing whether it's increasing or decreasing. So 1 can't be true. Does f of x have a relative minimum not at an endpoint? Well, again, so let's change the window here a little bit. Let's just only look from 2 to 10, which is what we care about. And let's go from like -2 to +2 for the y value, so we can kind of zoom in and see what's happening here. So you see the derivative starts off negative, and then it's positive, so we're going to have a local minimum, and then we're going to have a local maximum. And it's not an endpoint, so this is definitely true. It's going to be right here where the graph first crosses the x-axis. So right there. Some glare there. My apologies. Do we have 3 points of inflection? It looks like it. It looks like we've got 3 zeros here, where the second derivative is negative then positive, and then negative and then positive. Yeah, so I think that is also true. I think 2 and 3 is going to be the correct answer. All right, 44. 2 to go. The region in the first quadrant enclosed by the graphs of these two functions is revolved around the x-axis. Let's graph this, see what this looks like. Y equals x, I'm in the first quadrant, so it's this guy. And then y equals 2 sine of x. So it's going to start here, and it's going to like do something like this, roughly. So it's this region here that we're talking about. We would need to find this point of intersection. That point of intersection is, to find that, we would set x equal to 2 sine of x. And that is something that we can't do by hand. So we'll find that graphically or using the solver. Then I want to revolve this around the x-axis. And so if I do that, I'm going to be left with a bunch of washers, right? And so the area is going to be the integral from 0 to whatever that number is that we're going to find in just a second. It's going to be pi times the outer radius squared. The outer radius is 2 sine of x squared. Minus pi times the inner radius squared. The inner radius is x squared. Okay, so there's our setup. We need to find that point of intersection and then integrate over the appropriate region. So, how do we want to do this? Should we graph? Let's do it graphically. So y equals x, and y equals 2 sine of x. Let's graph. Oops. Yeah, we can change the window. Let's do x's from -1 to 3, and y's, yeah, that's probably fine. There's y equals x, and here's our sine function coming in. So I want to hit F5 to find the point of intersection. First curve, second curve. Lower bound is like somewhere to the left of this point of intersection. Upper bound is somewhere to the right. And that point of intersection is approximately 1.89549. Okay, so then, go back to the home screen. We want to integrate, so F3, integrate. Let's move a pi outside here. So pi times the function I'm going to integrate is 2 sine of x squared. So that's, 4 sine of x squared minus x squared, and then comma x, comma 0, comma 1.89549. Close it off, hit enter. I'm getting 6.678, looks like D. Cool. Last one. Y is x e to the x. What's the nth derivative? Ooh, this looks like a fun problem. Okay, so this one we got to just do some pattern recognition. I don't think I need my calculator anymore. I got this. Okay, so the first derivative, y prime, by the product rule is going to be 1 times e to the x plus x times e to the x, which is the same thing as 1 plus x times e to the x. Okay, what is y double prime? Product rule again, you're going to get 1 plus x times e to the x plus 1 times e to the x, which I believe is 2 plus x times e to the x. Oh, I see a pattern already. Boom, it's got to be B. Got to be B. All right, let's check our work. Let's check our work. 31. Where am I? I'm on exam 2. 31. B, then D, then A. Awesome. And then A, B, C. Awesome. And then D, B. Awesome. And D, C, C. Awesome. And then C, D, B. I got them all right. Yes. I'm wonderful. I got a 5 in this thing, no question. All right. See you soon.